we present gDNA towards generative detailed neural avatars. Creating virtual humans today requires expertise in graphic software and can be time-consuming. In this paper, we propose a method for the task of generative modeling of human avatars. By learning a manifold of 3D humans, our method can generate diverse and detailed 3D humans, with various identities and clothing, with fine and realistic geometric details, and under explicit pose control. To achieve this, we build an implicit multi-subject articulated model. We model clothed human shapes and detailed surface normals in a pose-independent canonical space via a neural implicit surface representation, conditioned on two latent codes, Z-shape and Z-detail. We then deform this canonical representation to a target body pose theta and size beta via a novel multi-subject implicit linear blend skinning module. This enables the comparison of the generated shapes with real-world posed scans, and thus allows training of canonical shapes and skinning weights without direct supervision. To capture the statistics that underlie realistic clothing details, we propose an adversarial training scheme in which a 2D discriminator is applied to 2D normal maps. To backpropagate the adversarial loss to the 3D normal field, we establish 3D to 2D correspondences via an implicit surface renderer. Previous methods rely on many scans of a person to create an individualized avatar. In contrast, we use scans of many people, in many poses, to train a generative model from which we can sample new people. Our method disentangles clothing shape, wrinkle detail, body size, and pose. By changing Z-shape, we can generate various clothing and human shapes that are beyond the discrete set of training samples. The nearest training sample is shown on the right. By changing Z-detail, we can generate different pausable clothing details for the same garment and human shape. We can also adjust the body size by changing betas. In addition, we can animate the generated human with unseen poses, even those beyond the training pose distribution. By randomly sampling from Z-shape and Z-detail, we can generate diverse human shapes. These shapes can be animated using existing motion capture databases. Here is another set of samples. Finally, we interpolate between the Z-detail and Z-shape of the training samples during animation. Note that the shape changes smoothly, showing that our method learns a smooth latent space of human shapes and details. Compared with the nearest training samples, our method generalizes well to unseen poses and can generate new identities. Thank you for watching.